Lesson 1-2, Patterns and Sequences. In this lesson, you learn to extend sequences. Let's take a look at example number 1 right away and see how this works. Let's take a look at this and study the pattern below. You have a square with the bottom corner, left corner has been shaded, okay, for 1. And the shaded triangle went up from 2. Now went to the right for 3, went down for 4, and went to the right again with 5. Now went up again on 6, and it's asking us in letter A, draw the next 3 figures in the pattern. So if we follow the pattern of where the triangle is going, okay, the pattern consists of the squares of one corner shaded. Corner that is shaded is rotated in a clockwise direction. The next 3 images are drawn below. So obviously the next 3 images would be the shading will be on the right, then down and back on the left. Okay. So you may find the pattern. For example, the 7th square may be the same as the 5th square, the 8th square may be the same as the 4th square, and the 9th square may be the same as the 3rd square. Okay, so that'll give you a better idea of what an extension on how to do patterns. Okay, let's take a look at example B. And example B is saying draw the 35th square of the pattern. And if we follow what this is saying, okay, the 7th square may be the same as the 5th square, the 8th square may be the same as the 4th square, and the 9th square may be the same as the 3rd square. Okay, so if we follow that pattern, it repeats after every 4 designs. Since 32 is the greatest number less than 35 that is divisible by 4, the 33rd square will be the same as the first square. Okay, so if you look at the pattern right here, and if you notice, it repeats after every 4 designs. Okay, so you simply get a number that is divisible by 4, the highest number that's divisible by 4 that's close to 35, and that is 32, and it should be less than 35. Okay, so if you now have 32, okay, that means that the 33rd square now will be the same as the first square, because the 32nd square will be the same as the 4th square. Okay, so the 33rd square will be the first square. Okay, and that's how you analyze this. This is how it looks like. This is your 33rd square. Okay, this is your 34th square, and therefore this is your 35th square. So you don't actually have to draw every single box to be able to find the 35th square. You can analyze it using what we did here in letter B. Okay, so in this case now the 35th square will have its upper right corner shaded. Okay, so a little bit of a twist on patterns like what we've learned in the past. The numbers 2, 4, 6, 8, 10, and 12 form a pattern called a sequence. A sequence is a set of numbers in a specific orders. The numbers in a sequence are called terms. So the number 2 is a term, 4 is a term, 6, 8, 10, 12 are all called terms. So in example 2, you're asked to find the next 3 terms in each sequence: 7, 13, 19, and 25. Of course, we need to study the pattern in the sequence 7, 13, 19, and 25. And we know for a fact that you add 6 every single time you go to a new term. With that in mind, okay, we each term now is 6 more than the term above it, and we add 6 to 25, which will give us 31, and add 6 to 31 give us 37, and add 6 to 37, which will give us 43. So the next three terms in this sequence, okay, are 31, 37, and 43. Let's take a look at letter B, 243, 81, 27, and 9. Let's study the sequence, the pattern, the sequence. 243, 81, 27, and 9 are all, okay, when you get 243 and you divide it by 3, you get 81. 81 divided by 3 is 27, and 27 divided by 3 is 9. Or you multiply them all by 1/3. If you multiply 243 by 1/3, you get the same result as if you're dividing by 3. So each term is 1/3 of the term before it. So you simply multiply 9 by 1/3, you get 3. Multiply 3 by 1/3, you get 1. And you multiply 1 by 1/3, you get 1/3. So the next three terms are 3, 1, and 1/3. Okay? One of the most used strategies in problem solving is looking for a pattern. When using this strategy, you'll often need to make a table to organize information. Okay? And that is a good way, that is one good problem solving strategy, is create a table. Okay, let's look at this example. What is the number of diagonals in a 10-sided polygon? Okay. First things first, draw a 10-sided polygon and all its diagonals. Okay. Drawing a 10-sided polygon and all its diagonals will be difficult. Another way to solve a problem is to study the number of diagonals for polygons with fewer sides and look for a pattern. Before we even start discussing this problem, we need to understand what a diagonal is. Okay, so a diagonal is something like this. It connects two non-adjacent vertices. So when you talk about a diagonal of a square, it only has one diagonal, because it is the only line that you can create, that you can connect two non-consecutive vertices. So in a square, obviously, there are 4 vertices. Okay, one vertex, second vertex, third and fourth vertex. Okay, and that's what the diagonal is. Okay, it connects two non-adjacent vertices. So in a triangle, if I ask you how many diagonals are there in a triangle, the answer would be 0, because all the vertices are, okay, in a triangle, all the vertices are consecutive, and that's the reason why there are no diagonals in a triangle. Okay, going back to the problem. Let's draw this out and let's see if we can find a pattern. Triangle has no diagonals. A quadrilateral's 4 sides has 2 diagonals. Okay, if you consider, okay, this other vertex right here, this will have another diagonal connecting to the other vertex. So a quadrilateral has 2 diagonals. Okay, a pentagon, 5 sides, 5 diagonals, and a hexagon has 9 diagonals. Okay, so the important thing that we need to look at are the number of sides and the number of diagonals. 4 sides, 2 diagonals, 5 sides, 5 diagonals, 6 sides, 9 diagonals. Okay, and let's see how they relate to each other. Okay, if you put them on a chart, you can see the number of sides and the number of diagonals. Okay, so you have 3 diagonals, 0, 4 sides, 2 diagonals, 5 sides, 5 diagonals, 6 sides, 9 diagonals. Okay, and so on and so forth. Okay, so if you have 7 diagonals, 7 sides, 8 sides, 9 sides, and 10 sides, how many diagonals will those polygons have? So if you notice, the pattern is you add 2, add 3. Okay, so what's going to happen next is that you need to add, okay, 4 to the other side, and then you add 5. That becomes 15. So a heptagon has 14 diagonals. An octagon has 20 diagonals. Okay, and so on and so forth, all the way to a decagon, which has 35 diagonals. Okay, so a 10-sided polygon has 35 diagonals by using the chart. Okay. Sometimes a pattern can lead to a general rule that can be written as an algebraic expression. This is an example of inductive reasoning. Inductive reasoning is used to make a rule after seeing several examples, and we discussed this, I think, in 6th grade and 7th grade as well when you talk about inductive reasoning. Okay, good real-life example of inductive reasoning is that it rained Sunday, it rained Monday, therefore it will rain on Tuesday. Okay, you are creating a rule after seeing several examples. Okay, so we can apply this to what we're doing right now in math. Study the following pattern. Write an algebraic expression for the perimeter of the pattern consisting of n trapezoids. Again, you need to know what a trapezoid is. A trapezoid, okay, is a quadrilateral with exactly one set of parallel sides. Okay, so in this case, let's take a look at our trapezoids. One trapezoid, 5 units. Okay, two trapezoids, 8 units. Okay, is the perimeter. 3 trapezoids, 11 units. Again, when you talk about perimeter, okay, perimeter is the sum of all the sides, and that's why this is 5. 1, 2, 3 plus 2 is 5. 1 plus 1 plus 2 plus 1 plus 1 plus 2 is 8, and so on and so forth. 3 trapezoids, 11 units. 4 trapezoids, 14 units. And if we create a chart, okay, to analyze what we have, the number of trapezoids and the perimeter of each. So we put them on a chart. One trapezoid, 5 units, okay, all the way to 4 trapezoids, 14 units. And if we look at the pattern of how that goes, we add 3 units every single time to the trapezoid. Every single time we add 3 units to the perimeter of the trapezoid every single time we add a trapezoid. Okay, and following that pattern now, okay, for one trapezoid, perimeter is 3 times 1 plus 2 or 5 units. 2 trapezoids, 2 plus 2 are 8 units, and so on and so forth. We discussed that already. So we simply extend the pattern. Okay, so for 5 trapezoids, it should be 17 units. For 6 trapezoids, it should be 20 units. And for n trapezoids, it will be 3n plus 2 units following the pattern we just created. So this is what we call inductive reasoning. Okay, we are using several examples to create a rule. So in this case, the algebraic expression 3n plus 2 represents the perimeter of this pattern with n trapezoids. Okay, and finally, the counterpart of inductive reasoning is what we call deductive reasoning. This type of logic, okay, that uses a rule to make a conclusion. Suppose your teacher says there will be a quiz every Tuesday, and today is Tuesday, then you know by deductive reasoning that you will have a quiz today. You did not observe a pattern to make your conclusion. Example 4. So when you talk about example 4, is example 4 inductive or deductive reasoning? Okay, so in example 4, since you are seeing several examples before you make a conclusion, that is inductive reasoning. Okay, you looked at several examples first. Another good example of deductive reasoning is if I say in class, if you miss 3 missing assignments, you will get a detention, and you know that this is your 3rd missing homework. Do you get a detention? The answer using deductive reasoning would be yes. Okay? And we've finished lesson 1-2. go on Google Forms, type a summary of what you've learned by responding to the objectives of the lesson. Type a question you might want to ask in class about this lesson as well. Thank you.